continuing with our look at graphs of motion, we're now going to look at displacement versus time. You'll notice with this graph now the horizontal axis, I've actually moved it up into the middle of the graph so that we've got both a positive displacement and a negative displacement. The reason for that is that now whether it's positive or negative becomes important. So with a distance versus time graph, the distance will always be positive. For displacement, we can now have a negative displacement, so we need to make sure we can have a negative part of the axis. One other thing that's important to note here is when you're talking about displacement, if you're using a negative, you need to make it clear what that negative actually means or what it relates to. And in order to do that in this case, what I'm going to say is, I'm just going to make a note over to the side here, that positive means in front of the observer or the person who's making these measurements, and negative means behind. So that just clarifies what the directions are, what the positive and negative directions are here. Could be to the left or to the right or up or down, depends on what the scenario is. We're going to use positive means in front, negative means behind. We're still going to use that example of the dog that I mentioned in the last video. And so we'll start off looking again at the motion of that dog where it moved 4 meters in 2 seconds. After that 4 meters, well, after that 2 seconds I should say, it stayed still for up until 14 seconds. Now though, we're going to clarify that the dog wasn't actually just moving away from the observer. Once it had stopped up until 14 seconds, it then actually started to run back towards and then went past and ended up having covered a total distance of 10 meters. Now you'll notice here we've got a distance of 4 meters covered going away. We've then got a total distance of 6 meters covered coming backwards, so the total distance covered by the dog is still 10 meters. So this graph for displacement matches up with the distance versus time graph that we saw before. Notice now though that we have this this section here that's going to have a negative gradient. That's because as we saw with the distance versus time graph, velocity is the gradient of a displacement versus time graph, or can be found from gradient of a displacement versus time graph. And as I said, whether the gradient is positive or negative now becomes very important. That tells you something about the direction that's involved. As before, the average velocity is going to be calculated from the just using the final position. So it's not the distance anymore, it's not how far it's actually covered, it's just the position at the final location. So average velocity is calculated using the final position. I should mention here as well that this example is only in one dimension, so sort of a straight line motion. And so it makes it a little bit easier. If you start getting into 2 dimensions, it's a little bit more complicated, but still just the final position over the total time taken. So with the final position, in this case, it looks a little bit strange in this scenario, because now the final position means that we're looking at this line here. So the final position is actually -2 meters and took a total of 20 seconds. So the calculation for that would then be that the average velocity would be the change in the displacement over the change in time, and in this case it's gone a total displacement of -2 meters in 20 seconds, and so that would give us a velocity of -0.1 meters per second, or you could interpret that as being 0.1 meters per second backwards, I suppose, so behind or backwards. So that would be the average velocity. The instantaneous velocity similarly to instantaneous speed, is calculated at a particular point in time. So if we use the 18-second mark at t is equal to 18 seconds, if we go back to the graph again and have a look at the point at 18 seconds, we're now dealing with this point here, and again we'd use the endpoints of that line segment there and there. So the first point there is 14 seconds, 4 meters, and the last point is 20 seconds with -2 meters. So they'd be the coordinates that we would use to calculate the instantaneous velocity at 18 seconds. So in that calculation, our change in displacement is then going to be given by -2 minus 4. So that's the change in the displacement over the change in time, 20 minus 14. And that gives us -6 over 6, which is equal to -1 meters per second, or another way of expressing that would be 1 meters per second backwards. Notice, if you refer back to the previous video, the speed at 18 seconds was 1 meter per second. Notice here that the instantaneous velocity at 18 seconds is also 1 meters per second. It's now that we've got this direction associated with it being the negative. So there's a little bit of extra information that you get from a displacement versus time graph, showing the direction that's associated with that motion as well. The next video will then start to take this a step further, and we'll start to look at other quantities, and then we'll develop those. We'll have a look then at velocity versus time graph and speed versus time graphs as well.